Welcome everybody. Thanks Maria for accepting our invitation to talk here at the CosmoVerse series. Maria Giovanna Dainotti is assistant professor at the National Astronomical Observatory of Japan. Before that, she was in Stanford as Mobinosh Fellow, Fulbright Fellow, Marie Curie Fellow, American Astronomical Society, and Miniatura Fellow, while in the meantime, she was assistant professor at Jagiellonia University in Poland. Her research interest is the study of the gamma ray bursts, statistical methods for determining selection biases, and the application of gamma ray bursts in supernovae cosmology. Today, she will present on the statistical assumptions on the distance moduli of supernovae 1A and its impact in the determination of cosmological parameters. Maria, you can start, please, when you're ready.
Thank you so much, Eleonora, for inviting me today. It is my pleasure to give this presentation. I would like to start with saying that this is quite a challenging topic because it involves several bits of knowledge, both from the theoretical and observational side. Okay. So the first question that we would like to ask is what are the fundamental cosmological parameters that we can infer, and then the Hubble constant, the total matter density, the dark energy density, and the equation of state parameter. And of course, this is in the flat lambda CDM model, but we can extend this reasoning also for non-flat models and for models that allow the curvature not to be zero. Then we have to face now for almost a decade the severe problem of the Hubble constant tension, which ranges, and it says that there is a discrepancy between the values between the early universe and late universe of the Hubble constant, which, as we can see here in this sketch, ranges from value around 65 up to value that are around 77 if we consider also the error bars. And of course, if you would like to see, this is taken from Dainotti et al. 2021 with a few cases. But if you would like to have an updated picture of this sketch, you can see at the paper of Eleonora in 2023. Now, there are several explanations for the Hubble constant tension. Both are from the theoretical side and for the observational side. And here we tackled this problem from a different approach in these two papers. And there are also other papers we have been working on the more on the theoretical interpretation of this tension. Now, what we did practically was to divide the Pantheon sample which is a collection of 1,048 supernovae in 3 and 4 bins that are ordered in redshift. Then we continued binning them in 20 and 40 bins. And the Pantheon sample release has been taken from the paper of Skolnick et al. 2008. Now, what we did was to try to understand where there is an evolving trend of the H0. And of course, we could mimic this evolution with a given function. Now, the function for the evolution is this function that I'm showing here. It's a pretty standard function that has been used for GRBs and supernovae, but mainly is a good function for small redshift, for observation at relatively small redshift. While you could have a larger, different function, more complex function, if you consider high redshift sources like GRBs and quasars, but the difference between the results when you consider different evolution does not change. So that's the reason why we picked this evolution. So one could wonder, okay, what happens if you choose another evolution? Of course, you would need to refit the data and check your adopted evolutionary function. Now, in this function, we have h tilde 0, which is the value of the Hubble constant at redshift 0, which we should believe that it should stay the same at all redshift. But then if we think that there is an evolution because there is difference between low and high redshift values, then we can mimic this evolution with this alpha parameter. So the question is, how many sigma away we can consider this evolution to be non-zero? and or whether there is practically no evolution from the data. So what did we do was to take the formula for the distance, the observed distance moduli from the supernova. This is expressed through the modified trip formula, and it is also present in the treatment in Skolnick et al. 2008. We have here the absolute magnitude for a reference supernova in the B band with given a stretch and color 0. Then we have the peak magnitude, observed peak magnitude in the B band, the stretch x1, the color C, and the host galaxy mass extinction, and the bias correction according to the treatment in this paper. Now, the parameter alpha and beta are actually derived by the fitting. And how can we connect the theory with the observation? So we have the defined theoretical distance moduli, which depends, of course, on a given cosmological model. And then we can just apply the chi-square, defining the differences between the observed distance moduli and the theoretical distance moduli. Now, of course, this evaluation, the chi-square, can be used with any probe. And here we use the C matrix that includes both the statistical uncertainty that are in the diagonal part and the systematic contributions, which are in the off-diagonal part. So I would like to pose a caveat here because maybe if you compare with some papers in the literature that they do not use the full treatment of the C matrix, then you may have slightly different results. And then, of course, the delta mu is the difference between the theoretical and the observed distance modeling. Now, if we apply also the baryoacoustic oscillation contribution, then the chi-square will be the sum of the contribution of the two chi-square. And here, instead of having the distance moduli, we have this co-moving distance, and again, we have the difference between the theoretical distance and the observed distance. And this is the definition of the co-moving distance. Now, what are the cosmological model adopted in this paper? As I already mentioned, here we consider that radiation is neglected, the curvature is neglected, so we have the ΛCDM model and also the W0WA CDM, in which we consider that the equation of state parameter is not equal to -1, but can vary. And it's a function of the redshift with the parameter W0 and WA according to this equation. Having said that, we could then show the results that we have for the ΛCDM model for 3 and 4 bins. Now, these redshift bins have been constructed in a way that for each bin, we have the same number of supernovae. But of course, this criteria can change. And actually, we are thinking about to use different criteria, for example, the same volume. So this will give different number of supernovae in each volume, but then the volume will be the same. For this approach, anyway, we are using this analysis, and we fix the value of H0 to the value of 73.5, which is the value of the Pantheon plus release. This is for requirement of our referee. So we can see that there is a decreased trend for the ΛCDM model and also for the W0WA CDM model. Now, of course, if you change the value of the H0, because this analysis has been done with the Pantheon, which by construction has the value of H0 equal to 70, then if you change the value of H0, you have to change also the value of M, or the absolute magnitude, accordingly. And that's why we here reported the value of the absolute magnitude. Now, if you consider the 4 redshift bin, here you have the analysis on the panel below. And the results are compatible both for 3 and 4 redshift bin. Now, if we consider then the W0WA CDM model, then again, we here present also the 20 redshift bin and the 40 redshift bin. And here we have how the alpha parameter changes at the change of the bins. The treatment is the same also for the lambda CDM model. Now, it is obvious that we have for larger number of bins, we have larger values for the error bars on the alpha parameter because we have smaller number of supernovae in each bin. So, of course, this is expected to have that, and that's why our, let's say, favored criteria for the binning is to live with the 3 and 4 bins, but this analysis in 20 and 40 bins has been done especially to show that regardless of the number of bins that you choose, you still have this evidence, mild evidence for this evolution. And now, if we summarize here the results, we see that for, as I said, for a given value of the h tilde 0, then we have to fix the value of m. And here we are also, this is the alpha sigma alpha, so it is going to tell you how many sigma you are away from the 0 value of alpha. And so you can see that in 3 bin, you are at 2 sigma, then you have similar results, slightly smaller for 4 and 20 bin, and again 1.8 sigma for 40 bins. Now, the interesting point here is that we decided to extrapolate this to I redshift, so the redshift of the highest galaxy at that time observed at redshift 11.09, to observe if this trend exists still at this redshift, how we would see. And then we extrapolated again at the redshift of the CMB, so at the last scattering surface, redshift of 1,100. Here the units of the Hubble constant are in kilometers seconds megaparsec. And here you can see that although the error bars are large, actually we can see that this trend shows that it continues to decrease very slowly, and it reached the value actually of the Planck result at 67.5. Therefore, we could say that if the evolution exists at all redshift in the same way, then we could practically reduce the tension. And this is on the right-hand side, we can see the table with the tension reduction at 54, 66, 68, 57% level. So you have a range at least from 54 to 68% level in each bin. You have a reduction of this tension. Of course, at larger value of the bins, then you have a larger value of the error bars. Now, if you consider this the flat, but W0, WA lambda W0, WA CDM model, then you have a similar value of the reduction of the tension between 55% and 72%. And here we computed the difference as 1 minus XF. XF is the value of the Hubble constant at 0, minus the value that you would have from the fit at 1,100 divided by the root square of the errors that you have in the two cases. And Xi is defined as the difference between the Cepheids instead and the CMB value. So to check how much we have this reduction. Now, in the next paper, we decided to add also the baryoacoustic oscillation and to check what the situation would look like. Also, we had several comments from the community that the one possibility was that this trend was due to the fact that actually we were varying only one parameter at a time. So the reason we did that, because if there is a mild evolution that actually it's somehow masked out by other evolutionary trend, then if you change all parameters altogether, you are unlikely to see it unless it is, again, a strong evolution. But if it is a mild evolution, then it can be easily washed out. That's why we did this approach. And actually, the 3 and the 4 bins analysis were at the level in which the full analysis of the Pantheon sample for the omega m values would not change. So that's why we chose these 3 and 4 redshift bins initially. Now, if we vary instead H0 and omega m, but we don't need really to vary omega m in a large redshift range. In fact, we picked Gaussian priors for omega m so that this 2 parameters contribution would not be washed out. We still have this evolutionary trend at the level for 3 bins at 2 sigma, and at 3 sigma, for the flat lambda CDM, including the BAO, it is at 1.2 sigma, and for the without BAO, barring H0 and omega m, it's at the level of 2 sigma. You can see, in fact, that the trend is still present. Now, if you consider instead the 3 bins with the W0, WA, CDM model plus BAO, then if we have without BAO, we have a trend of 5, or difference 5.7, and if you consider BAO also, you have similar trend 5.8. So now we are still investigating why there is this deep difference, so this steep trend in these cases, and we do not have an answer yet. But now I already anticipated actually this slide, because I was telling you why we have gone then in 2 dimension rather than in 1 dimension, because we really wish to have that the fluctuation will not dominate, and that's why also the number of bins initially was put as small. And here it is this Chevalier-Linde-Polaski parametrization that takes into account of this W0, WA, as I mentioned before. Now, we put a constraint for W zeta greater than -1, but of course also phantom models can be considered for W less than -1. And what about testing this model with the Usabiki gravity? So we could think about the fact that maybe there is actually this difference in the values of the Hubble constant. So there is actually this evolution. This is not due to selection biases. And if it is the case, then maybe we could apply this Usabiki 2007 model. But if this trend would have been determined by the Usabiki model, then we could have seen this trend disappear after the application of this model in the distance luminosity. But this is not the case. So it seems that although there are many tests of this is one model among the possible models, this is not the final answer for us. So another possibility that actually it is an intriguing one that was investigated by Nicholas et al. In 2021. It's about the fact that actually there is an evolutionary trend for the stretch factor x1. So what does happen if you have an evolutionary trend for the x1? It means that your alpha parameter that I showed earlier would also change, possibly with this parameter. Then if you have a change of this alpha parameter, then all of the linear combination that you have in the previous equation may change. Therefore, this could be the cause of this trend. And of course, it is very important to continue checking this, although I know that many groups have done multiple checks for selection biases, but I think the question is still open about that. And one caveat that I would like to pose, and this is also the start of the next part of my talk, is that basically we cannot neglect the fact that when we add more data to any sample, whether the supernovae, the GRBs or the quasars, then we might need to check again the distributions and the conditions of applicability for these samples for our cosmological models. And here it is the summary of what I already explained about the possibility of these 2 solutions, either some astrophysical or selection biases that are still yet to be investigated, beside even the stretch parameter, or additional theory of gravity model. But now, what about looking at the tension for another perspective? Are you ready about that? If you're ready, then I think let me tell you that, of course, we are in an era in which we really strive to reach precision cosmology. But are we really sure? So we are building a larger telescope. Of course, we are trying to fine-tune the methods for crafting the sample. But what about the assumptions of the likelihood that we use for the application of cosmology? So the common assumption are the Gaussian likelihood of the supernovae, of BAO, quasars, and GRBs. But the question that we would like to ask is that are all these valid? And actually, the answer is no. So the supernovae, BAO, and quasars actually do not fulfill the Gaussian likelihood, but only GRBs they do. And I will tell you possibly why it is so. Now, here in this picture, you have the number of supernovae in the Pantheon sample, which is normalized at the error bar. And here you have in green the normal or Gaussian distribution fit. And in orange, you have the logistic distribution. Here, the same panel for the Pantheon plus normalized. And here you have the Pantheon plus and Pantheon distribution. So you could see that the distribution are different, and we tested this with several means, so with the kurtosis and with also the Anderson-Darling test and the Kolmogorov-Smirnov test. So all these tests, all these statistical tests show that this distribution are different. Now, of course, one could argue about the fact that these tests are very strict, very severe. So the more data you have, the more this test may not pass. But regardless of this, we need to make sure that we know how much skewed is our distribution. And the details of the distribution may matter then in the result of the cosmological analysis. So now this value, you see that there are this distribution are actually they're having pretty heavy tails. But now I would like to define what it is the logistic and the student distribution and tell you what actually it matters for the cosmological analysis. So we know that, of course, we would like to have as many data as possible, because the more data you have with the given scatter of your relationship, let's say, of your trip relation, if you have a given scatter, then the more supernovae you have, the more you can constrain the cosmological parameter with a better measurement. So, I mean, smaller uncertainty. But now the point is that here not only the number of data are important, but also the scatter of the relation. Here in the logistic, we have the scale factor, and which is related to the variance in this way. So the smallest is the scatter of your relation, then the better it is your more accurate is your determination of the cosmological parameters. And here, for the logistic distribution, we have the x-axis, that is the average, it is minus 0.004, and the scale factor is 0.08. And for the Gaussian is actually 1 order of magnitude smaller, and sigma, it is 0.14. And it is, I already showed that this is in green. And this is the probability distribution function for the t-student distribution. Here we have the gamma function, and this is the variance, how the variance is related to the Ni parameter, that is the degree of freedom. So in the cosmological analysis, we leave this parameter also free to vary. And we have applied statistical tests as the Akaike criterion information, Bayesian criterion information, of course, to compare this distribution, because this distribution are different numbers of parameters, so we cannot simply compare the chi-square. And even doing this more refined test, we could see that the analysis favors this new likelihood. But now, what are the consequences of using this new likelihood? So this is with LG, we indicate the Gaussian likelihood for the several probes. And in a moment, also, I will tell you some problems or challenges that we face with the gamma ray bursts, actually, to get them as being cosmological standard candle. I will not have a lot of time to discuss about the quasars, but of course, if you're interested, we can discuss during the question time or at another time, during another time. So here we have three values for the definition of the evolution. I already mentioned that we picked one function for the evolution. Now, in this case, we are not making the evolutionary function for the H0, but rather we are considering the possible evolution for the parameters of the quasars and of GRBs in this analysis. So we keep the same likelihood here of the Gaussian likelihood for the supernovae, but we use different evolutionary function for these probes. And now we have tested a flat ΛCDM model with a curvature that it is different from 0, and also the flat WCDM model. What we can see here, actually, we have compared the Pantheon plus with the Gaussian likelihood and the Pantheon plus with the new likelihood, indicated with the LN. So now what we can see here is that the value of the new likelihood preferred slightly larger value when you consider varying evolution. So varying evolution means that our function of the evolution vary together with the cosmological parameter. And this is something that we have tested in a more refined way in a paper for quasars, Lennart et al. 2023. Then for fixed evolution, instead, we consider this function at a given value of cosmological parameter. But because the error bars on the function for the evolution are pretty large, then this does not really matter. Now, the takeaway of this, and I will tell you in the next slide more summarized, is that we have larger value for the Hubble constant in the new likelihood, but practically the error bars have been reduced. With this, the uncertainty on the parameters have been reduced. And the same for the flat ΛCDM. Now, going to the reduction of the uncertainty on the parameters, then we have that the logistic distribution is reduced by 43% with the logistic distribution, the value of omega m, from 0021 to 0012, and 41% from 034 to 020 for the Hubble constant, respectively. Then, if we consider the T-student distribution, this reduction in the uncertainties is up to 42% from 0019 to 0011 for omega m, and 33% for H0 from 024 to 016. Now, in this analysis, we did make vary omega m and H0 together, but we also tried to leave one parameter fixed and the other free to vary. One parameter free to vary and the other fixed. So we tried several approaches. And if we would like to see this in a more visual inspection, then we would see that the Gaussian likelihood of much larger contours. This is 68 and 95%. The darker color is 68, and the faded color is the 98%. Then we can see that the logistic distribution for the Pantheon and the T-student distribution for the Pantheon plus sample, they have indeed a smaller range of the error bars. You can see that there is also a shift in the value of H0. So you see that the T-student distribution marks a shift at higher value. Compared also, this is the same that happens also for the Pantheon sample. So you have a shift for larger value of H0 and a slightly smaller value for omega n. Now, what can we do at this point? Because I have already anticipated that the point is that not all the probes have the Gaussianity assumption. Actually, so far only gamma ray burst. Can we actually use this IZ probe to cast light on the tension? And I would like now to go, although I anticipated the result, I would like to go a step back to say why it is important to use several relations in gamma ray bursts as well as quasars, and what we should look for these relations. So gamma ray bursts are, as you all know, are flashes of high energy photons in the sky of typical duration of few seconds, and they are divided in several classes. But now the prompt emission has undergone to several scrutiny for problems with the selection biases. So it is advisable to use properties of the plateau emission, because you have this flat part here that it has undergone to less variability compared to the prompt emission. And here the relationship that we use for the afterglow emission is the luminosity at the end of the plateau emission and the time in the rest frame duration. So this is an anti-correlation. So it means that the more energetic is the plateau emission, then shorter it is its duration, or dimmer it is the plateau emission, then longer it is its duration, but the energy reservoir of the plateau usually stays constant. Now, if you belong to the GRB community, you probably have heard about this motto that we have been struggling with the GRBs for more than 20 years. So how to use GRB as a standard candle. This is very challenging because light curves vary very widely. And if you have seen one gamma ray burst, actually you have seen only one. And that's why we wanted to investigate both the classes of gamma ray burst, but also the which part of the gamma ray burst we should favor. So these are I like calling this problem the GRB zoo, because you have several classes of gamma ray bursts. I mentioned that we have the short GRBs, short duration GRBs, that have the duration of the prompt emission less than 2 seconds, the long GRB greater than 2 seconds. Then we have the other classes. X-ray flashes have the ratio between X-ray fluence and gamma ray fluence greater than 1. Majority of the long GRBs are associated with supernovae, but only if they are observed at a small redshift, supernovae 1bc. However, there is also the short with extended emission classification, in which the duration is less than 10 seconds, but the properties of the spectrum are similar to the short GRB. So it is a mix between short and long. And the debate about the progenitor is open. So why did I dive into this? Because for the application of cosmological candles, it is very important to understand what it is the physical grounding of this relation. So if you do not have a precise meaningful relation in terms of physics, then you can practical mismatch among the classes. So this is a caveat of not to use relationship with all many classes, and also a caveat that it is important to pinpoint which energy emission mechanism or which model could actually favor your relationship. And here there is a bunch of several relationships have been discovered in the prompt emission, and here it is the timeline of the relation that I just mentioned. This is the two-dimensional relation done in X-ray and some extension in optical, and then the three-dimensional relation. This is the relation that I've been using for the result that I showed. It is after selection biases have been corrected. So these two-dimensional parameters, these two parameters have been added to these two parameters. We have added the peak prompt luminosity, and here we have this 2D and 3D relation. Now, I would like to also put another caveat on the usage of the relationship as distance estimator and the forward fitting model. Because if we use this relationship to obtain the redshift, this relation depends on cosmology. So basically, you have one circular problem. Another problem here, if you can see my arrow, at high redshift, for large variation, for a small variation of the redshift, actually for a small variation of the distance luminosity, you have actually a large variation of the redshift. So that's why this relationship can be used for inferring cosmological parameters, but it is not advisable to use as inferring the redshift. And now I would like to present this relationship for which we use the cosmology together with the other probes. And as I said, we need to remove these other classes and leave only the long gamma ray burst with a relatively flat plateau. Now, if we do that, then we reduce considerably the scatter, and this, in fact, becomes to be one of the tightest correlation in the literature compared to the other relationship. Now, I've told you that this relation has been discovered in X-ray, but this relation is also holding for optical, and for the cosmological application, we are also using this in optical. In fact, the forecasts that I'm going to tell you in a moment are both for the X-ray and optical. Now, I told you about I anticipated already that that for BAO quasars and GRBs, actually, we have a problem for quasars and BAO, because also the Gaussian distribution is not the best distribution, but we have the T-student distribution and the logistic distribution for the quasar respectively, while for gamma ray burst, Gaussian distribution seems to be okay. So all the derivation that has been done previously, it is still holding, because the Gaussianity assumption is correct. And as I said, we are using this relation in X-ray and optical for deriving this analysis. Now, I mentioned about this new statistics and all the configuration, how all these configuration have reduced the uncertainty. So when we consider I already mentioned in the other table how this uncertainty play a role, but also we can see that the variation, the percentage variation, we have all a negative value. It means that we have all reduction. And the central value, as I mentioned, of H0 are combined with all the problems together, are closer to the value of Supernovae Pantheon plus sample. So in one sense, we are going toward saying that most likely Supernovae 1A value are favored, but on the other hand, the bad news is that the discrepancy becomes slightly larger in this regard. What can we do next? Because all this analysis that we have done, actually, they consider the simultaneous fitting of the cosmological parameter with the correlation parameter. And we can use the cosmic chronometer as calibrator for the fundamental plane relationship. So currently, again, if we compare this, why are we using this relation? Because if you consider, for example, one of the prompt emission relation, the Epike ISO relation, but also the Yonetoku relation, you see that usually the scatter ranges between 0.20 and 0.54, depending to the sample size, and up to 0.55. But here we have reached a scatter of 0.18 plus minus 0.09. So this scatter is comparable with the tightest analysis that we have done with the fundamental plane relation. Also, after we have taken into account of the evolutionary effect. Therefore, because if we consider a small sample that it is up to the redshift of the cosmic chronometer, we still have a small scatter of the relationship, we can extend this also at high redshift, and this is something that we are planning to do. Then the question is that what else do we need to do for cosmology? Of course, we need to play around and try to find out new and tighter reliable relationships, or actually trying to tighten up the existing relationship, because we have quite a number of relationships. And if you would like to check all relationship updated up to 2017, 2019, you can also check my book published in IOP. We can increase the sample size, as I already mentioned, this will help, but also, again, tighten up the relationship. And we can have cosmological independent approach via low redshift probe through the extension. But as I already mentioned, we should also push forward for the physical interpretation, the connection with the theory in the quest for the standard set. So how we are going to do that? If we would like to increase the sample size, we need to have in mind what are the numbers we need. So now on the right-hand side, we have the optical fundamental plane. When we consider that the error bars are undivided, so it means that you have the full range of errors, uncertainty on your variables. And you can see that around 2000 GRBs, or even less than that, you can have very small uncertainty on omega m, so a very good precision. However, if you consider a sample in which this is reduced, then the uncertainty are reduced by half. Then you can be settled also for a number which is almost half of it, so with 1,000 of gamma ray burst. Now, if you are interested, you can check the several tables we had in this paper. And I would like to summarize here this result. So if you are happy with the, of course, we would like to compare how much GRBs would be reaching the precision of the supernovae. So if we consider the precision of Conley in 2011, so more than a decade ago, then we can reach this precision easily now, because we only need 67 GRBs of the tightest one, and we can reach with the machine learning analysis with reducing the error bars on the parameter, and this can be done with the light core reconstruction. Machine learning analysis is the analysis for which you would obtain the redshift inference, not through the forward fitting method. That's why I told you earlier, please do not use the forward fitting method. I also did try myself, but it was not successful. But it's better to use machine learning analysis, and this is what we are going to tackle with collaborators. If you would like to reach the Betul et al. 2014, you can reach just in 2 years from now, again with this method. And if you would like to reach the precision of Skolnikov 4 years ago, then you would need to wait 18 years from now. But this is a pessimistic, not an optimistic inference, because I've been considering that there will be the same number of observations that we have today, which most likely will not be, because we will have maybe more facilities. And also, this analysis does not take into account the fact that when you combine light curves together, so this has been done already 2 years ago, but we are now working with a large group of people for building the largest catalog of optical observations, and we are merging many observations together from several telescopes, ground-based facilities mainly, but we have crafted the strategy. So in doing that, we will have more data points in the plateau emission, and then we will have immediately more number of data. So this forecast will be updated after the catalog is released. And another option, as I said, we could test other models. So the closure relationship model is giving results of the scatter of the samples, which are comparable to the one that we have. So we are planning to use probably the magnetar model to infer a smaller scatter in the future. And again, how we can increase this sample, as I said, we could have the redshift inference through a series of papers that have been published, and some of them are also in submission. But now I would like to show you, I think I may have additional few minutes. So this is the results that we have for the inference of the redshift for a generalization of 151 gamma ray bursts. That's why I told you that we will have more redshift after the sample is generalized. And in these days, we are actually increasing also the sample size. So here, this is the training set. And this is the generalization set. So we have this redshift that can be added for our cosmological purposes. As I said, we are going to increase the ladder for the calibration with the cosmic chronometer. And another point is that what else can we do? Because I've been speaking now about gamma ray bursts, but we can combine also these enhanced statistical methods and enhanced samples for gamma ray bursts with the probes of quasars to tighten up this relationship. And actually, we did also for the quasars in this paper. So we reached already in this paper the precision of the supernova, and we did a sigma clipping technique, which actually reduced the scatter of the relationship. In this case, is the luminosity in X-ray optical luminosity relationship, and these results show us that if we perform this method, we have 983 quasars that have a very, very small dispersion, and with this reduced uncertainty, then we have reached the same precision of the Pantheon sample. Now, this is the analysis. So you can see very, very interestingly, we actually have two minima here at the value of omega m, that it is close to the expected value, but also for larger value of the number of quasars, we have even a smaller value that it is almost considerable, almost consistent with a quasi-de Sitter universe. And this is something that we have been possibly discussing with this alternative theory. But now, again, we can do more, because the problem is that, okay, the sigma clipping technique is one of the statistical techniques, but what about if we change the strategy? And we also did that with multiple methods. So there are other two papers in which we apply this different technique. In this paper, we apply the Huber regressor technique, which is a technique that discards directly the outliers in the distribution without using the sigma clipping, and this is called the robust regression. And in this case, we found a comparable sample size, I mean, like around maybe 50 or more sources, and we have also much smaller dispersion. So we can also use with this sample the quasars as standalone objects. And here, in fact, we can check the value of omega m and the uncertainty for a fixed value of H0. And this gamma, beta, and delta is the scatter, and gamma and beta are the parameters of this relationship. Now, going to the last paper that was very recently published about this other new beginning method. This is something that we wanted to dig more about this methodology, because in the previous method, we did bin the sample so that the number of sources would be similar to one bin to another. In this case, instead, we call what it is a bin size maximization technique, which actually was crafted by Alexander Leonard, one of the students here in the paper. And this enhanced the bin division. So then we use not the Huber regressor, but we use the Tilsen regressor method. So it is a even more robust method that does not imply Gaussianity assumption of the distribution. And in this case, we have yet another sample for the quasars, but still comparable. And here again, we could determine quasars as standalone standard candle. So then the maximization algorithm actually gives the idea of the precision cosmological measurement. Also, we have this omega m parameter versus this n and the sigma clipping procedure. So the larger it is the sigma clipping procedure, so it means that the larger is the number of sources that you have, then the smaller will be the precision on omega m. But then it's you have a fluctuation, and then inside this region you will have the optimized cosmological standard candle. And of course, I would like to apologize because the time did not allow, but there are so many papers in the literature that also face the challenge of selection biases in quasars. And this is not a comprehensive status of the situation, but just more a review of the paper that we did within collaborators and my group. And now, if we would like to investigate the fact that in this case we have smaller value of the omega m parameter, then we could explain this also by the f of r theory of gravity. In this case, we have this f of r theory that actually it's very similar to the we can see in the red line, and the lambda LCDM model is in the orange line. But this is also possible within this theory to explain better this small variation of the value of omega n. And now my time is up, so I would like to ask you to stay tuned because the story continues. It's not really finished. So the next step is to use all the standard candle improved and extended sets to cast light on the new precision cosmological parameters, plus to try to understand if we could obtain this quasar subset independently with the statistical analysis. So thank you so much for your attention.
Thank you. Thank you for the very nice talk. Do you have any questions? Yeah, Vanina?
Yeah, thank you. So thanks so much for this nice talk, and it was very interesting. I would like to come back to the results that you obtained when using only type 1a supernovae for your cosmological fits. I didn't quite understand how you can break the degeneracy between MB and H0. So my first question is, the samples, Pantheon and Pantheon plus samples that you are using, are they combined with the Cepheid Hauss distances, so has to have a precise estimate of H0 at null distance, or is that just cosmological samples that start at redshift around 0.1 or so?
Okay, so thank you for your question. So here in this paper, because it was published in 2021, we could use only the Pantheon sample. And in this paper, we use the value of H0 that it is fixed, as you know, in the paper of Skolnick et al. 2018. So we use then the M value, which is here, that corresponds to this value of H0. Because of that, we could not break the degeneracy and H0, because one value, if we leave H0 free to vary, however, the initial value for H0 must have a M that is fixed.
Yeah, of course. Yeah.
And here, you know, this I skipped to mention actually that this evolution of the H0 is similar to evolution of this MB parameter. So thank you for your question, because this is relevant to the fact that other people also earlier saw this evolution of the M parameter. And basically what we did is to go the step forward. The next step was to see how this would revert with the evolution of H0. Now, the plan regarding your question about the Pantheon Plus is that we would like to repeat all this analysis with the Pantheon Plus sample, but including also the statistical, the new likelihood, because this analysis has been done with the previous likelihood. Yeah. And yes, I would like to mention something else, because another point here is that in the news in the Pantheon Plus sample, I showed this different statistical likelihood, but this is also due to the fact that in the Pantheon Plus sample we have duplicates from several samples. So now, while in the GRB community and in the catalog that I'm building, we do not consider duplicates in you know, different observations. Therefore, we try to combine the light curves so that the entity of one light curve on one GRB is one. Now, although from a statistical point of view, it is correct to say, okay, if they are different, even though it is the same supernova, we assume them to be different how to say, different entities in the same in the way that we are adding more supernovae compared to the supernova entity that we have. But my question, that it is also aligning a little bit on the ontological side, is that we can introduce actually biases on the categorization of the supernova. So when we choose a sample, we are already somehow introducing some bias in the analysis. So now the how to say, the to-do list, the idea is to discriminate among the samples, remove the duplicates, and find out if there are differences between the statistical analysis between one sample and the other.
Okay, but coming back to those plots, since you said that it comes from fits which have a fixed value of MB and AGO, what is the meaning of this AGO which is plotted here?
No, I'm sorry. M is fixed. H0 is free to vary.
It's free to vary. Okay,
yes,
so
yes.
it's a real H0. But if I see this, my interpretation is just that what you are seeing is that when you are maybe reducing the low Z part of your sample, you are not as I would say your result on AGO changes, and in fact you just don't know how to really measure AGO. I cannot interpret this as an evolution of AGO, but just as a bias of the method.
No,
because you don't.
If the method has a bias, then you would not see that this method is recovered also for 20 and 40 bins. While however you have this result also for 20 and 40 bins. So we tried several bins, 5 bins, 10 bins.
Yeah,
50
you told us, yes. Well, just a last comment. I would be more convinced by an evolution of AGO if your method here, this method that you are depicting here, was cross-checked on simulation. You have a simulation, you know which AGO you inject. You just simulate a synthetic Hubble diagram. You know exactly what is AGO in that, and you do the exact same analysis, and you tell us what you find.
Yes. Actually, thank you for your comment, because the plan is not only simulate the real observation, but also because there is an imbalance in the Pantheon plus sample, which of course it's naturally, because you see few supernovae at high redshift, but because of this imbalance in the sample, then we could not with observed data identify this trend unless we do simulation, and we are now investigating technique, machine learning technique, they are called, balances the sample, and we would like to check how much this effect can change according to balancing differently the sample. But thank you. Yes, this is the simulation. It's something that it is in our plan to do.
Okay, thank you.
Thank you so much.
Thank you so much, Eleonora, and thank you.